Welcome back to the Organic Chemistry playlist. Today we're going over the reactions of alcohols. Specifically, we're looking at the review. In the next video, we'll look at what we call oxidation of alcohols. So making that oxidation state more positive. So the many ways that we can react in alcohol is, remember, SN2, SN1, E2, E1. We're also going to look at a couple new reactions that are kind of, they are SN2. It's SOCl2 and pyridine, and then phosphorus tribromide. And that we'll see for primary and secondary alcohols, those can attach halide groups. So let's get into it, shall we? All right, let's start with the really niche reactions. Remember, for E1, let's say we have this kind of alcohol, right? So we have a tertiary alcohol. That's going to promote SN1. Let's use acetone, or sorry, not acetone. We want to use a protic solvent, so let's say H2O. And we know that we could do an SN1 reaction with, say, hydrobromic acid. Okay, so we have hydrobromic acid here. We've all seen how this mechanism works. Hopefully you did. These lone pairs reach out to the hydrogen, giving bromine a negative charge. And remember, we get that good leaving water group. So we have water, it's ready to leave, so then we follow it up with the bromine. Well, actually, before any of that happens, this leaving group is just going to up and leave, right? So we're going to lose water. And then we have a tertiary carbocation, and then that's when your bromine comes in. For SN1, remember, it's a unimolecular process, not a bimolecular one. So that leaving group actually leaves first without that kind of initiation from bromine. And then we're left with, in this case, a tertiary halide. Okay, now let's move on to SN2. Remember, SN2 is a bimolecular process, so as that leaving group is leaving, that nucleophile is coming in at the same time. This is going to be favored for secondary. Well, E2 would be preferred, but secondary can still happen. And then, of course, your primary alcohols. So I'm going to just, to keep things simple, we'll take a secondary or primary alcohol, and let's react it here. So it turns out we can use any sort of acid halide here, not an acid halide, but a halide and then bonded to a hydrogen. In this case, it best happens with hydrobromic acid. It does this here, makes a good leaving group. Okay, so we get that there. And then bromine comes in and does backside attack and kicks out the water. We lose water in this step. And we're left with our final product, which is bromopropane. That's the second time I have failed to say that word in this series here. Now, since we've seen with bromine, how about chlorine? Well, iodic acid, that will do it well, but we'll see that for HCl, it's not very good at occurring. So we have to promote it a little bit, and we use this species called zinc chloride. It's an ionic species. So you'll definitely have to do this in water, but it will let, what's it called, SN2 happen. So basically, and I'm going to elaborate the zinc here. All right, so our hydroxide, and I'll erase that so we don't get confused, erase that arrow. What we see is going to happen is, well, if this is negative, this is positive, it's most likely going to attach to that. It's going to kick off the chlorine, because chlorine is happy with a negative charge. Okie dokie. So we have our zinc chloride there attached to our or our hydroxyl group, and that makes it an even better leaving group than this one here. This leaving group with our water, when chlorine's attacking instead of bromine, so when chlorine's coming in, it's going to have an easier time reacting with our compound with our zinc chloride. So keep that in mind. That's why we use zinc chloride there. Alrighty, and just like I was saying, SN2 occurs, so we're going to take that chlorine that we omitted, and it's going to go like this. And our chlorine. Alright, so that's our product via SN2. Let's get into the second reaction. So let's say hypothetically that you're in the lab and for whatever reason you can't seem to really get a good yield. Well, or like the reaction is very slow or isn't happening to an appreciable amount. You got to speed it up. Well, you can use a tosylate here, tosyl chloride, and basically what this will do, and we'll just draw it out. And all the reagents you need is that tosyl chloride. You need pyridine as a base, and then you need a sodium halogen. And in this case, we'll use bromine, so we'll say sodium bromide. So I'm going to draw out our tosyl group. Remember, that's what that is. And we'll draw it as such. And, drew sulfur. Remember that the reason that this creates amazing leaving groups, as you might remember, is because of the high resonance stabilization. There's two oxygens that can kind of juggle a negative charge. There's an aromatic ring that can juggle charge. It's really nice, and it makes for a wonderful leaving group. So basically what happens first is oxygen comes in. It's going to attack that sulfur, and it's going to kick off the chlorine. And what we get as a product, or not as a product, as intermediate here, I should say, it's going to be this, and we'll simplify it as tosyl, TS. Alrighty, so we know that this has a positive charge, and pyridine comes in with its electrons. About to sneeze. Oh, nope, not today. I'm a little sick. Remember that pyridine is this here. It's just a nice little resonance stabilized base. It's really wonderful. So that comes in, and I'll just erase that. It comes in, steals that proton. Alrighty, now that tosyl group is ready to leave. So what happens next, now that we have everything neutral, is we're going to get some backside attack. So let's say we have our bromine from sodium bromide. That comes in and just does backside attack, and it kicks this group off. And now your product, you'll be left with this here. So you would have bromine. And our tosyl group now, so if I were to draw our tosyl group as well, we'd have our sulfur here, aromatic ring, this. We now have this molecule here, which is extremely stable. This will never come back and attack like that. It will never reverse the reaction. So you get pretty good yields when you use a tosylate. So if you have problems in the lab, try this reaction. It should help out quite a bit. Okay, so for our last SN2/SN1 reaction, I want to look at the reagents of SOCl2 and phosphate tribromide. Alright, so what do these reagents do? How are they useful in the lab? Well, they're just convenient reagents so we can turn alcohols into alkyl halides. So let's make an alcohol here. Primary alcohol works fine. And you need to use a base, so we're going to use our pyridine base. Alrighty, and we're going to use our SOCl2. And same thing here, but no pyridine for that. So it's just phosphorus tribromide. And what you'll see that you get are these reagents here. Alright, so you will most likely in your class be expected to know the mechanism. So I just want to get into it here. We'll do SOCl2 first, and then we'll get into phosphorus tribromide. Okay, so it's not too terrible of a mechanism. Has some similarities to the last one that we just saw with the tosyls. So yeah, sulfur, double bound to an oxygen, chlorine, chlorine. Basically that oxygen comes in and kicks off a chlorine. Quite simple here. Now we have this. Okay, and then our pyridine comes in and steals a proton, leaving us with this here. Oh, and I forgot to say, yep, there's a positive charge here. I sometimes just forget to draw that in, so I apologize. And then we have this intermediate. Now, this group here is a wonderful leaving group. It's resonance stabilized, so of course, when it is kicked off, it's not likely to go back. So if we just bring in our chlorine that we kicked off, we do backside attack, kick off that group, and of course, there will be some resonance stabilization there. So let's draw this in now. We have a alkyl halide, specifically an alkyl chloride. So that there is a wonderful reaction. There's the full mechanism. To kind of review, oxygen picks up that complex there, but kicks off the chlorine, and then deprotonation to stabilize the molecule, then backside attack, which causes the leaving group to have high resonance stabilization right there. So if we were to cut that off, you'd see that oxygen is in resonance, that oxygen is in resonance, not likely to reverse and go this way. So kind of like the tosyl chloride thing, if you don't have tosyl chloride, you can always use this reagent here. All right, this one is a little more simple. You don't really need that deprotonation from pyridine for it to be a good leaving group. It just kind of is a good leaving group with that hydrogen on there being an alcohol. So we'll see how that works. Let's draw in our alcohol over here. Let me scoot the screen over a little bit. So we have our alcohol, phosphorus tribromide. Alrighty, so again, lone pairs, gonna pick up phosphorus tribromide, kick off a bromine. You'll see that's kind of a neat thing. These reactions are kind of the same. They'll do that, attack a complex and then kick off of something off of it, and then it comes back later. So phosphorus, and just to keep things simple, Br2, right? We won't draw to elaborate on all the bonds. Okay, and then that bromine just simply comes back and right. This has a positive charge. I did it again, guys. Positive charge there. That bromine comes and does backside attack, kicks that group off, and we're left with our final product, our alkyl bromide. So, yep, those are two reagents that we can do SN2, SN1 with, depending on how sterically hindered this is. Like if it was that, it would probably do SN1, but I digress. So, okay, so for our last reactions, we're going to look at the elimination E1, E2. They're kind of the same, so I won't spend a crazy long time on it, but let's just say we have this molecule here, and we have an alcohol. Remember, we can use H2SO4, and we can heat that mixture, and we should get an elimination. So remember how this occurs, O4SH, for example. some lone pairs, reaches out, grabs a hydrogen. And now we have a pretty good leaving group. Water is happy to leave and not come back. So that's exactly what happens here. So with heat in this reaction, we can come back with the, we can take water, for example, or we could take our conjugate base, doesn't matter, but assuming that you're doing this in water, you're probably going to have a lot more water. So what happens, there's a hydrogen sticking out here. Remember, it's going to go to the more substituted carbon. It wouldn't attack up here. Nope, you're not going to get an attack up there for elimination. You're going to go to the more substituted side, which is right here, where you have 1, 2, 3 carbons. So hydrogen gets deprotonated and eliminates into an alkene. Alrighty. So you get that one as your major product. Pretty much I'll review there. Okay, so if we have this compound here and we want to make it happen even better than this reaction that we just saw, we can do kind of a similar thing as we saw with the tosyls. If we bring back tosyl chloride, it will help us do some elimination a little better. So again, we need to use a weak base like pyridine. So it reaches out, kicks off the chlorine, nothing too crazy yet. Okay. And then we'll simplify that to tosyl. All right, now pyridine comes in and it's like, yo, give me that hydrogen. Oxygen's like, you got it. So now we can use a base like an ethoxide or any oxide. Really any base would work here, but it has to be strong enough to do elimination. So we have our OTS. Okay, and for our elimination to occur, yeah, let's just say we have ethoxide, right? And we have a negative charge, comes in, and eliminates and kicks off that group, giving us the more substituted product, the Zaitsev's product, as they say. And this is your major product. Again, if you want no irreversibility, that tosyl group is heavily resonance stabilized and is a good option. So that's it. That's going to be it. Hope you guys enjoyed. That was just a review of SN1, SN2, E2, E1, and a few little interesting reactions sprinkled in there that helps reactions go forward favorably and to an appreciable amount. So hope you guys enjoyed.